Okay, and here's another question. The topic this time is binary trees. The question: write a function that accepts a binary tree t and returns the amount of nodes with only one son. Two things I noticed in the question. It doesn't say it's a binary search tree, it's just a normal binary tree. And it has to return nodes with only one son. Basically, we're saying with only one non-empty son, because obviously every node has two sons. Even a leaf has two sons, which happen to be empty. But we understand what means one son, meaning that there's actual tree there. Okay, so pause now. Do a pause and answer the question. After you sort of looked at the question, you might have answered it, or you might have thought of ideas. What I'll do now is I'll think aloud. I'll talk aloud and see how I'm going to about answering the question. So let's take this tree as an example. So basically, I have to see. There's a few different cases that I have to think about. One, what happens if it's an empty tree to begin with? If it's an empty tree, then I have to return 0. Okay, that's quite obvious, because it doesn't say in the question that it's a non-empty tree. So I have to take into account all the possible cases, and one of the cases is, of course, an empty tree. Then I have to think about, okay, when I get to a leaf, what's a leaf? A leaf are all these. They have no sons at all. So that's going to be part of my, I will have to return. When I get to a leaf, I'll have to return 0 because it has no sons at all. Then I have to deal with cases like, okay, what happens, let's say I'm here on this subtree, with 6 being the root of this subtree. It only has left sons. It only has a left son. 6 only has a left son. It doesn't have a right son. Okay, so I have to deal with that. I also have to deal with a case like this, where there's no left son, but there is a right son. And of course, the more general case is, what happens if there's a left son and a right son? So, if we take that last case, that's probably the easiest one to look at. Okay, the number of only sons, or single sons, let's call it, in the whole tree that is with 9 as the root, is how many are in the left subtree, plus how many on the right subtree. How many here? How many on the left subtree? Plus 1. I have to count him because he is this 6 is a node with only one son. So let's take a look at a possible solution. Here is my algorithm, single sons, and if the empty tree t returns 0. If it's empty, return 0. That's true. That's what we said. If it's empty tree. And if I'm at a leaf, how do I know if I'm at a leaf? If empty tree of the left and empty tree of the right, I'm here. I go here to the one leaf here. And if this is empty and this is empty, that means I'm at a leaf. Nothing to count, so I return 0. And now, if the empty tree of left and not, notice here, not empty tree of right, meaning that, yes, okay, we found, let's take this example here. Left is empty, but right is not empty. So what do I have to return? How many are on the right? Plus 1. Why plus 1? Because I have to count him. And the opposite case would be like here, where it's not empty of left, but it is empty of right. So I want to know how many are here, plus 1, because I have to count him. And then the even more general case would be, okay, what happens if there's 2 sons? So, okay, fine. Here, all these have 2 sons. I'll say, very easy. Return to me, please, the amount of single sons on the left-hand side plus the single sons on the right-hand side. And this is the answer, a suggested answer to the question.